You have already looked up the specific gravity of a number of substances, including normal hexane, which was Sg of normal hexane to be 0.659. We would like to get the density of normal hexane from it. We denote density by the Greek letter rho, and if you want to type this letter, type R, and then with Microsoft Word you can change the font to symbol. That way you can type rho. And also we learned that the specific gravity is defined as rho of the substance, in this case hexane, over the rho of water at 4 degrees. Rho of water at 4 degrees, we learned that to be 62.43 pound mass per foot cube if we take the American engineering system. And then here we want the normal hexane density. This is equal to 0.659. So we have the density to be equal to 41.1 pound mass per foot cube. Next, we have a beaker with 0.5 pound mass of water, and we want to get the volume. Density is equal to mass per volume, and in here I have the density of water. Volume of water would be the mass of water, which is 0.5 pound mass, divided by density of water. Let's take that 62. Let's use that 62.43 pound mass per foot cube. And I am going to get the volume water as 8.009 times 10 to the minus 3 foot cube. In this case, I just took the significant figure of this number to be 4, and I assumed 0.5, which is given, is a defined number, so it has infinite significant figure. Next, we have the question, what does Sg tell you? And for this, we can have an observation. Let's pour normal hexane into a test tube. Suppose that this test tube has normal hexane, and then add water to it. And because normal hexane is a hydrocarbon, water and hydrocarbons don't mix, so they make 2 layers. And in order to differentiate, let's add a blue dye to water, so we have this blue as water. We will see that in the test tube, water goes to the bottom, normal hexane stays at the top. That is because the specific gravity of normal hexane is 0.659 and the specific gravity of water is 1, and the density of normal hexane is 41.1 pound mass per foot cube, while the density of water is 62.43 pound mass per foot cube. The lower density stays at the top, and this is what Sg tells us. Next, specific gravity of glycerol, we can look it up in the table B, and as you see, it is 1.260. Because it is a dimensionless quantity, it is the same number in all the systems of units. Now, what is this subscript 50? That's because when we define the specific gravity, we defined it as the density of the substance, in this case glycerol, over density of water. Temperatures for these densities are defined. Look at the heading of this table. It is 20 degrees. It means that this density should be at 20 degrees and water should be at 4 degrees. There are some exceptions in case the data is not available. Those exceptions are specified in the table. So in this case, when we have this number as density, we know that the density of glycerol has been measured at 50 degrees Celsius, unlike the default value of 20 degrees Celsius. Finally, in this exercise, the last question is, why isn't the specific gravity of carbon dioxide not given in the table? And that's because it's a gas. If you take the liquid at some temperature and you increase the temperature, the volume and density of the liquid will not change that much. So it's not appreciable. So it's worth to tabulate it in the system. However, gases are much more sensitive to increase in temperature. So at this temperature, if the volume of gas is this much, then it's going to increase a lot at a higher temperature. Therefore, it's not worth to tabulate the density of gas in tables. Instead, we are going to have other ways which we will address in the future to get the properties of gases.